Welcome, everybody. Our today's Compute Ontario Colloquium is about the emergence of WebAssembly, or Wasm, in scientific computing. These are the things that we are going to cover today, a little bit about Wasm, and then MScript, and a little bit about WebGPU, and then we have a live session to demonstrate all these things. So let's dive straight to why there is a need for yet another web technology. For many researchers working in the field of scientific computing, sooner or later, there come circumstances that urge you make a methodology, an algorithm, a software, or even a training and exams available for a wide range of users. That usually ends up with a list of common options like this: source distribution or multi-platform binaries, container images like Docker or Apptainer, or web application. As you go down the list, the burden is transferred from the user to the developer. So for example, in case of source distribution, the user is responsible for finding a system to run the software in addition to compilation and installation. But for the web app, no build or installation is needed, and the app also runs on the server. As a bonus, users can run the web app from anywhere using any device that has a browser. So if we'd like to target a large number of users, which is usually the case, web app would be the preferred choice. But we should overcome some challenges associated with a web app. First, there are portability issues. While most scientific software are written in languages like C++, Fortran, or Python, the language of the web is JavaScript. An implementation process, if not impossible, is often overwhelming and requires substantial efforts. Second, you need an external server to host the web app 24/7. And last but not least, as the number of concurrent users of the web app increases, it can bring the server to a halt. It's really common. For example, if you design a web app as a exam server, when the number of students go to 300, it becomes chaos unless you have a really powerful server. But there is a new kid on the block that can address these shortcomings, and that's nothing other than WebAssembly, or Wasm. That brings us to Wasm 101. So what's Wasm? Wasm is an emerging technology that allows developers to run high-performance, low-level code in web browsers or standalone virtual machines. Under the hood is nothing more than a binary code format that serves as compilation targets for other programming languages like C++ and Rust. And this binary code can run on any platform that has a compliant Wasm virtual machine and can be run at near native code performance, which is important for us in scientific computing. Wasm modules are isolated from the rest of the browser runtime, reducing the risk of malicious code compromising the user's device or data. Wasm is hardware, language, and platform independent. So you can compile once and run anywhere. There's no installation required. It can achieve near native code performance, and its modular design supports the creation of large, complex applications built from smaller, reusable components. These two features make it suitable for scientific computing. Wasm is a typed stack-based machine. What does that even mean? Here you can see disassembly of the same C code to both x86 and Wasm. You can see here that for Wasm, in this assembly for Wasm, you have the type for variables. For example, this one is a 32-bit integer. And the other thing is that rather than using registers like this one in x86, all the things happens using the stack. Stack machines are simpler than register machines as they have no need to manage and allocate registers. But what are Wasm modules? Wasm modules are units of deployment, loading, and compilation. They are stateless and side effect free and can declare imports and exports. Multiple modules can interact within a single application. And a little bit about memory model that Wasm uses. Wasm is a hardware architecture rather than von Neumann, which means linear memory is separate from code. Each Wasm module has access to a single resizable array of bytes known as its linear memory, which is a flat array of bytes, and can grow by a multiple of the page size, but cannot be shrunk. But a binary code format and a virtual machine is not enough for developing a functional program. By default, Wasm can't do anything. You need something like a standard library. There are two common options here. For web embedding, you can go with Emscripten, which relies on web APIs and JavaScript, is more mature, and provides POSIX and libc and libc++ on top of it. It can also provide sound, graphics, mouse, and keyboard handling using SDL library. For standalone runtimes, you can go with WebAssembly system interface or WASI. It has POSIX-like interface, not complete POSIX, and it's a work in progress and provides libc and libc++ as well. So as far as there is a compiler for your language of choice that supports Wasm, you can generate a Wasm binary file, and then you can either run it in a web browser or use one of the standalone runtimes like Wasmer to run it without a web browser. This table summarizes some of the compilers for common languages in scientific computing that support Wasm as a target. As you can see, you get the best performance with Rust compiler. It's even more efficient than C and C++. And another thing is that starting from version 8, Clang support to directly produce code for Wasm. There are other platforms. You can see that I put the Jupyter here. It's not a language, but it's forced to know that you can now use Jupyter Lite, which is a WebAssembly version of Jupyter. And the good thing about it is that it runs on user's computer rather than on a server. Now let's get back to our problems with traditional web app and see how Wasm can deal with them. With Wasm, you can recycle existing code with near native performance, but without the hassle of rewriting in JavaScript. There is no need for a dedicated external server as well. You can use one of the free services like GitHub Pages for public repositories to deploy the files automatically using GitHub Actions. We'll see how to do that during the live session. And finally, as the web app runs on the user's device, there would be no scalability issues. But WebAssembly brings its own new challenges. Scientific software have a long list of dependencies and interconnected libraries, all of which must be ported to WebAssembly first. That makes porting a code more complicated, requiring lots of trial and error. And finished products may also require some web development to handle user interactions, typically involving glue codes in JavaScript. Like any other emerging technologies, current implementation of Wasm has some limitations as well. For example, Wasm32 is limited to 32 bits and can access only 4 gigabytes of memory. Wasm64 is supported by some compilers, but most browsers currently don't support it. Or allocating more than 300 megabytes of memory is not reliable on most browsers. And this one is really, a shame for scientific computing. Support for threads with shared memory is on hold because it may circumvent browsers' mitigations for Spectre and meltdown security vulnerabilities. But it's on the horizon. Maybe sooner or later we have it. This last one is not important for scientific computing, but the Wasm doesn't have direct access to JavaScript document object model. But as I said, it's not really important for our use of Wasm. We are going to use Emscript 10 for today's live session, so a few words about it here. It's the oldest and most widely used compiler and toolchain for Wasm, mainly supporting C and C++, but more recent languages as well. It was designed primarily for web embedding, so it can generate all the glue files. It's based on LLVM and binarian, and supports pthreads on browsers that have implemented and enabled shared array buffers. So there is some hope about, parallel runs, at least using Emscript. And it can also convert OpenGL calls to WebGL. A good thing about Emscript is that it has some ports, which is a collection of useful libraries ported to Emscript. You can list them with show ports option while you're using MCC or M++ compiler. As you can see, for example, all boost headers are already included, and there are some other, libraries that if you want. So, for example, SDL2 is there, and you can use it, out of the box. Projects requiring more computing power can use a related but different web technology called WebGPU. WebGPU is a web graphics API that provides unified and fast access to GPUs. You can use compute shader code written in WGSL, the Web GPU shader language, for general purpose computing on GPU or GPGPU. This is achieved with the underlying Metal, Direct3D, or Vulkan system APIs. You can use Web GPU header file, which is included in a C API, to access all procedures and data structures of Web GPU. Currently, there are 3 implementations or bindings for the Web GPU native header. Fortunately for us, Emscript already has bindings implementing Web GPU header on top of the JavaScript API for web embedding. But Google's Dawn, developed for Chrome using C++, and Web GPU native, developed in Rust for Firefox, can be used for standalone apps. We don't cover Web GPU in today's live session, but that can be a subject for another seminar. Now let's change the gear to our live session. Here's the link to the repository we are going to use during the live session later. You can use this QR code for launching the web app in your mobile when it's time for it. So let me first switch my screen to okay. Okay, I think you can see my terminal window and also the repository that we need. But first, let's start with Mscript and set up on our computer. So my desktop is Windows. But like any other Windows, active in scientific computing, we usually use WS or Windows subsystem for Linux for day-to-day operation. So here is Windows terminal and having the on WS. So I'm going to install Mscript and first set up and install it on my home directory in WSL, but you can do it the same if you want to run it natively on Windows as well, but this way is much easier. So the first thing, you can go to getting started and start downloading and install. The whole thing is really easy because all you have to do is to just clone the Mscript and repository. So I do it in my home directory like this, and then go to SDK, and it says git pull, but usually you don't need it. It's a if you want to update, it's necessary. But after doing that, you can use MSDK, install. And if you want to use the latest version, you just say latest. It takes some time, but once it's ready, you can just activate it. And so one thing that I should do, because I was in a previous round, let me now have a new one while it's working. MSDK here, you can see the files. So when it's finished, I switch to this one to have a new environment. Now I can use MSDK activate command. Oh. And once you do that, whenever you want to activate the environment, you can source this one, or you can put it in your .bash rc. But for now, I just source it to have the whole environment. Okay, like this. Okay, once you've done that, to check everything is okay, and we have the MCC compiler, you can use MCC-V, which is the C compiler. And for C++ is EM++. And you can see the version and all the things. Now we are ready to do the things. Yeah, you can see the target triple here, which is Wasm 32, and vendor is unknown, and on Mscript. And if you use WASI, for example, this one changes to WASI, another runtime. But Mscript is basically for web interface. So let's go to I have some sample files here on my WinHome desktop. So a typical hello world C, which is you're all familiar with it, is like this. All you have to do to compile it is emcc and then hello.c, and you can specify the output file name like this. When you do that, it actually produces a Wasm file that you can directly run it using the node JS. So if I do node hello, you can see the hello world output here. But usually you want to run it in web browser. And if you want to do that, you can change the compilation command from this to this one. When you specify HTML, Emscripten generates all the necessary files to have this one run on the web. So you can see that now we have hello.js, hello Wasm, which is the Wasm file, and also HTML file to open it directly on web browser. Something that you may consider is that, okay, I can open this hello HTML in a browser, but because most browsers don't support XML HTTP requests, they can't open the other associated files. So we can try it, but because I am on the WSL to have Chrome running, I switch to, I have also Git bash here to Windows operating system. And if I want to run Chrome, I can use start. This is the same folder here, but I should have the complete path. So I can use start Chrome. I just want to demonstrate that what's wrong here when you run it directly in the browser. And then hello HTML. If you do that, you can see the whole thing, but it stops at the preparing phase because it can't open, it doesn't support XHR, and it can't open the other associated files. So the way that we can do it is by running a web server here. There are several ways of doing that. Let me go to this here. One way, if you have Python, for example, you can use Python 3 and then -m HTTP server like this. And you can go to the same folder here. And if you use the local host 80,000 and hello HTML, you can see the hello world here. But there is a simpler way to do that. Emscripten provides a runner, which is called mrun, that you can just use it to do the same thing much easily. So it's better to use that one. It automatically also opens the hello world for us. Easy peasy. But the next thing, this one is just plain one. You want to do more interesting things usually. You can find a CPP version as well, but it's more or less the same. Here is a SDL demo from Emscripten that prints some graphics. So let me just first show you this one. It's a really simple program that shows something, but we can do the EMCC and then using the hello SDL and specifying the hello SDL HTTP. And using mrun to run it like this. Let me close this one as well. Why I can't see it here? Oh, it went to another. Okay. Let me use it like this. I don't know what happened to my. Usually I should have it. It went to my other window, I think. But let's, oh, hello, SDL. Oops. Something is wrong. Maybe I put the wrong thing here. Let me try it again. It should automatically open it here. Let me see. Oh, it's trying to download it. Let me see what's going on.
Is it because you used the wrong extension? In the previous one, you used the HTML extension. Now this one, you use
Oh,
HTTP.
yes. Okay. Yeah. Thank you for that. I just put HTTP rather than. So if I do mrun hello SDL HTML now, it should work. Okay. Now you can see the output here, and you can also change to full screen like this. I don't know if you see it in the full screen mode using the Zoom, but it usually works. So this one is a sample one, but in scientific computing, we are more interested in running something like this sample, which is, we usually have it, which is calculating the pi. It's this compilation, you can find it in the web. You can see the whole thing here. Without any change, I can compile this one using the same procedure. So if I go EMCC and calc pi c, and then calc pi HTML, I can compile it. But there is a problem here. But let me show you what it is. When you do this, using the node, you can run calc pi. Oh, because you can see here the output is users. This one needs some input from the user, the number of tosses. So you can just specify it like this. And you can see that it's run and calculated the pi number and reporting the error. But the thing is that if you want to run it on the web, you should have a way to, pass these arguments from command line to HTML1. So if you want to do that, MScript 10 provides a way for doing this. You can specify mrun option while you are compiling. And when you do that, while using mrun to run this calc pi HTML thing, now as the next argument, you can pass all the arguments after this one like this. Without this option, you can't do this. So here, if you run it like this, You can see that it's run, and you get the same output here. So the good thing about MScript is that it simplifies these kind of things for you, and you can use simple, C or C++ programs to compile them and run it like this. But to have something more interesting, so we can also have some performance check, I decided to do something else here. This is the repository that I told you, and you can find the QR code in the thing. You can just go to github.com/arminms/gold2p to access it. It's an C++ implementation of Conway's Game of Life. It's one of the classic, cases of cellular automata, and it's really famous, and you can use it. But the good thing is that I can use this one to do also some performance testing to see how good it runs this. The good thing about this sample is that I made it in a way that you can compile it both on your desktop of choice and also WebAssembly using the same CMake interface. All you have to do is to just clone it and run it, but the WebAssembly version also published as a GitHub page. So if you want to see it in action, all you have to do is just click on this, and it will be run on your browser. It just prints a frame per second as well for performance testing. Usually on my computer is about 145, but now because I have Zoom going on, it's a little bit goes up and down. To prove that this code I actually run it in my browser from this side, but it's running on my computer. If I show the task manager here and go to thing, you can see that is 69% on CPU and 52 on my Intel GPU. Usually it's less than that. It is now because I'm running Zoom as well, and it affects that. So it's usually about 30% for GPU and 30% for CPU. If I stop it, you can see that this one is going down to 14%. So it's running on my computer rather than server. But you can compile it locally as well. So if I go to, I've already cloned it here to, if I want to run I can directly run the web version. So you can use the same command like this to compile it. But also you can use the CMake because it has the CMake version. To build the CMake version for Linux, I mean WSL, all I have to do is like this. But because I've already done the configuration and build, I just can run it. But to be sure that everything is in order, I just use CMake build to be sure that, okay. Oh, let me pull first to be sure that I'm on the latest version. And then, okay, it's ready. Now I can run it using build source. So this is the Linux native version, but it's running on my WSL. So it says that it's Linux. You can see that frame per second is about 57. So you may wonder why it's slower, WebAssembly version was faster because WSL is a virtual machine. So maybe it's not as optimized as the real Windows. But the good thing is that we can also compile the same thing because this one, using the same command, you can compile it natively for Windows as well. So here, if I go to, let me see, where am I first? Okay, if I go to source, I have goal2p here. Let me git pull again. Using the same command, I can build it on Windows as well. Okay, now I can run it using build. I'm not sure on Windows. The directories on Windows is a little bit different. So let me go. I should go to source, and then release. Okay, here. So if I run goal2p here, this is the Windows version. Oh, this is a different version that goes into full screen. I don't know whether you see this or not, but it's gonna make the things a little bit problematic for me. So I don't know if you could see that because it went to full screen. It was changed, but the speed or frame per second is still about 60%. I don't know. I couldn't find any right reason for that, but I think that there is a frame rate cap on Windows set for SDL to make it like this. To be sure, but I can't show this for you. I have a Linux machine. I try to compile it on Linux and see the difference between the native version and also WebAssembly version. On my Linux box, it's the difference between frame per second or FPS was about 10. So the native version was 10 frames more than the WebAssembly version. So it shows that the difference in performance is really marginal, and it's a good, you can say that it's near native performance. But I don't know why on Windows the native version is actually really slower than the WebAssembly version. You can also use the same link on your mobile because so if you go to this same link and click on this, you can run it on your mobile. On my mobile, which is a Pixel 6, the FPS is about 90, 91. So the good thing is that by having this, you can run your software anywhere that has a web browser like this. But the next thing that I'm gonna show, this, before doing this, switching to that, it's worth mentioning this sample is really good because there are several techniques that you can find here, how to build a code for both, desktop versions and also web version using WebAssembly. The all CMake files is here, and there are some techniques that I used here. So for example, how to load fonts and those things in WebAssembly and include it in your source. If you check this source, all of these techniques are here in this sample. So it's a good starting point that gives you a head start doing that. But another good thing about this project is that it has the necessary GitHub action files here to publish it. So if you go here to github.github workflows, you can find Wasm YML file or YAML file that you can use as a template for your project to publish it in GitHub. So it's really simple. It just switch to Ubuntu image and then check out the whole thing. And then it sets up the MSDK like the way that we did. And then it tries to make a public directory and compile the code here like this. You can, for your project, the only line that you have to change is this one to compile it and put it in a public folder. And then you use this one to, publish it to GitHub pages. So if I have another project, so let me show you how you can do it for your own project here. Let's say I want to make a new project. Let me go like this. I make a new project and named it as test or Wasm test. And I don't put anything in it. I just create the repository. And here are the comments. Now here, I just go, let me switch to my WSL here. I make a directory named Wasm test, going there. And let me copy one of the samples that we had, for example, hello STL, having some graphics here. Okay, so in order to publish it to this, I can follow these instructions here. So I don't want the README MD5, so I start with this. And then I just use git add hello STL. And then let's go with the rest of the things here. So now my repository is set. And if I go here, I can see it. Hello STLC is right there. The next step, if I want to publish it, this one, and access it, I need to have that GitHub action. So first, that file was in the cp command is like this. So I put it, the goal2p project, it was in .github workflows, and it was Wasm YM. So this is the file that I need to copy. But before that, I have to make a directory. So let me do that. So I should make this folder like this. And now I can copy this file to .github workflows. Okay, if I do git status, now I have a new file, but I should edit it. So I just go here to vid.github, more flows and Wasm. The only thing that I need to change here is this line. The name of the file for me was hello STLC. I put it in the same thing, but because I don't want any of these very related for that game of life project. So I can remove these files completely. And when it's done, it automatically copies here to the public. So I just have to save this one. And now if I do, let me see, yeah, git add that GitHub, it would be like this. So, but one thing before I pushing this one, I have to go to settings here and go to actions, general, and change this setting to read and write permissions. Because this is a GitHub action tries to write to the repository in GitHub pages, we should give it the right permission. So we save this. And now I can push it to GitHub. Oh, I didn't commit. Add Wasm YAML file. Now I push it. As soon as I push this one, it should start doing this action. You can see that it's already there and it's in progress. If I click here, you can see the deployment is running. We should wait till it finishes, because once it's finished, we can go here, because there is one more setting that we should do. While it's working, let me show you. You should go to settings and now go to pages and say that we want to deploy from a branch, but the branch that we need is GitHub pages, that these GitHub actions will produce it for us, but it's not yet there. So we will wait till it finishes. Is it still running? It takes some time, depending on the. Note that this one is running on GitHub, still running. Sometimes it's so fast, sometimes it takes. Usually this MScript installation takes a little while, but the build and deploy is pretty fast. So while this one is finishing, I wanted to show you, let me show you the Jupyter Lite. It's one thing that I wanted to show you here while it's working. Is both Jupyter Lab and Jupyter Notebook version for Wasm are there. You can see the repository here, and you can click and see the whole thing. I don't know that the link was here somewhere, but I can't see it. If you run it in Jupyter Lab, I should use this one. Yeah, you can see this is the Wasm version of Jupyter. It means that everything that you run here is actually running on your computer. There is the same thing for R as well. You can find the links on the slides and use it. But let me switch to this one and see it's still running. Sometimes it takes more. Let me go here. It's not finished. Okay, while it's working, let me show you another thing here. Next thing that is interesting as well is that in while it's working on this, let me put it here to see it. Let me change to source and go. Okay. If you change the source code, there are three settings actually here that you can change. One is resolution, and this is the cell size. I can reduce the cell size here to smaller ones to make it more, even more demanding. So if I save this one and CMake build, oh, and if I run it now, which is in build source, you can see the frame rate now down to 12, 13 from 60 because it's now the size of a pixel. In the web version, anytime you refresh the screen, it starts another word or another simulation that you can do it. But on desktop version, all you have to do is run it again. So let me see if it's still going on. Oh, finally built. Once the build is finished successfully, you can check it by going to see that if GitHub Pages is there, you can see it's actually there. And these are the files that are published. So the next thing that we can do is here is go to Pages here and say that we want GitHub Pages to be deployed. And once we've done that, it may take some time. Oh, actually, it's there. And then we can use, so for me, it's army.ms GitHub IO, and it was Wasm test. Oops. Test Wasm or Wasm test. Maybe it's not there yet. It's not there yet. So it takes a little bit to have this published. And once it's done, oh, I didn't save it. So you should save it. And once you've done that, it should work. No, Wasm test. It takes some time. But once it's done, usually when it's done, you can see it here like this. So if I show you this one, once the deployment is there, you should see the results here that is deployed. And then usually you can see the link like this in the website as well. Let me try again. Okay, now it's there. So we successfully published our Wasm file as well. I think that's conclude our session for today. I stop my share now, and I'm ready to answer your questions.